Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group. I will teach you Power System 3. In the previous video, I have discussed about economic operation of thermal power plant for lossless system. In this video, I discuss about economic operation of thermal power plant. In this video, we consider the loss of the power system, and we solve equation. Now in this video I will discuss about economic operation of thermal power plant considering the losses. Now this topic is included in module 2, economic operation of energy generation system. Also discussed about plant scheduling, transmission loss and penalty factor. In
economic operation of thermal system. Now in previous derivation we neglect the transmission losses, but in this case we consider the transmission losses. So in this case we consider the losses. Now in previous case we neglect the losses. Now however it's unrealistic to neglect transmission losses, particularly when long distance transmission of power is involved. Now a modern electric utility serves over a vast area of relatively low load density. The transmission losses may vary 5 to 15% of the total losses, and therefore it is essential to account for losses while developing an economic load dispatch policy. So it's obvious when losses are present, we can no longer use the simple equal incremental cross criteria, which we have derived in our previous video. Now consider a simple system in which all the generators at each bus are identical. Now equal incremental cross criteria would dictate that the total load should be shared equally by all the generators. But considering the line losses, it will be cheaper to draw more power from the generators which are closer to the loads. Okay. Now the load should be shared among the various plants when the transmission losses are accounted for. So what is our new constraints in case of if losses are there? So what is our new constraints? Our new constraints is I equals to 1 to m PGI minus summation I equals to 1 to n PDI minus PL equals to 0. So this is our new constraints. Now where m is the total number of generating plants. M is the total number of generating plants. And n is the total number of buses. N is the total number of buses. Now PGI is the generation of ith plant. and PL is the total system transmission loss. Total system, PL is the total system transmission loss. Transmission loss. Transmission loss. Now, to solve the problem, again we have to write the Lagrangian cost function, that is C bar equals to total fuel cost summation of I1 to M Ci Pgi. Now this is the total cost minus Lagrangian multiplier into the constraints. What is the constraints? I equals to M. This is the constraint function, Pgi minus Pd minus PL. So this is our total cost and this is the constraint function. We have to multiply it by Lagrangian multiplier, and this equation is the Lagrangian function. So it follows that for a given real load PDI at all buses, what is the unit? Unit is rupees per hour. Now it follows that for a given real load PDI at all buses, the system loss PL is a function of active power generation at each plant. So PL is a function of active power generation. Okay. If the power factor of load at each bus is assumed to remain constant, the system loss PL can be shown to be a function of active power generation at each plant. So that is, we can write PL equals to PL in the first bracket Pg1 power. PL is a function of output active power. Okay, now this is the optimization problem, and PGI where I is from 1 to M are the only control variable. Now this is in the optimization problem, and PGI from I to M are the only control variables. Now for optimum real power dispatch, the first derivative of the cost function should be equals to 0. So we can write here derivation of C with respect to output power minus delta. This becomes 1, and what is the value of derivation of PD? As PD is constant, so derivation of PD is 0. So from here we get 1. This is 0 minus delta PL by delta PGI equals to 0, where I is from 1 to M. Now from this we can write derivative of cost with respect to output power is equals to lambda 1 minus delta PL by delta PGI. Now what is the value of delta from here? What is the value of delta? We can write the value of delta is equals to dCi by dPgi by 1 minus delta PL minus delta PGI. So I equals to 1 to from 1 to M. Now incremental cost of ith unit into Li equals to lambda. I equals to 1 to up to n. Now what is Li? Li is the penalty factor. Li is the penalty factor. And what is the value of Li? Now what is the value of incremental cost? This is equals to dCi by dPgi. This is equals to incremental cost IC. And what is penalty factor? Penalty factor can be written as Li equals to 1 by 1 minus delta PL by delta PGI. Now this is the penalty factor. This is the penalty factor. Penalty factor of ith unit. Penalty factor of ith unit. And this term is known as incremental transmission loss. This term is known as incremental transmission loss. Incremental transmission loss. Transmission loss. Now this equation can be written as, IC, that is incremental cost, equals to lambda minus lambda into 1 minus, what is this? Incremental transmission loss. So this expression is known as exact coordination equation. This equation is known as exact coordination equation. Exact coordination equation. Now, it is clear that to solve the optimum load scheduling problem, it is necessary to compute incremental transmission loss for each plant. And therefore, we must determine the functional dependence of transmission loss on real power of generating plants. Now, these are the several methods, approximate and exact, for developing a transmission loss model. Now it is further written as lambda equals to IC into penalty factor. Thus the optimum generator allocation considering line losses is obtained by operating all the generators such that the product incremental cost into penalty factor equals to lambda, that is Lagrangian multiplier for every generator. Now, if the generator limits are taken into account, then all generators which are not at or beyond their limits are operated such that incremental cost into penalty factor, this equation for each of them. Now, the generators which are at or beyond their limits are operated at their limits as in the lossless case. Now, what is the physical significance of lambda in the case of losses? Now, next one is the physical significance of lambda in the case of losses. Now, for small change in the fuel cost, we can write delta C equals to I1 to M. Now this is our incremental cost. Okay. Now again from the exact coordination equation we can write lambda into 1 minus del PL by partial derivative of PL with respect to PGI. Okay. Now put the value of incremental cost in this equation. So this is lambda 1 minus delta PL by delta PGI into delta PGI. I equals to 1 to M. I equals to 1 to M. Now multiply the delta PGI. I equals to 1 to M lambda into delta PGI minus I equals to 1 to M delta PL by delta PGI into delta PGI. Okay. Now PL is a function of generated real output power, that is Pg1, Pg2 up to Pgm. Small change in delta PL we can write equals to I equals to 1 to M partial derivative of the PL with respect to PGI into delta PGI. Now this term is same as this term. So we can write delta PL in this place. So I equals to 1 to M lambda delta PGI minus lambda into delta PL. Now what is delta PD? Delta PD is equal to total generation minus total losses, that is equals to our demand. Total generation minus total losses equals to our demand. So we can write lambda into delta PD, because summation of I to M delta PGI minus delta PS equal to delta PL equals to delta PD. So this is equal to delta C. So lambda is equals to delta C by delta PD. Delta C by delta PD equals to lambda. So this is the physical significance of lambda. Lambda has the same significance as in the lossless case, that is lambda represents the incremental cost in rupees per hour. by incremental load demand in megawatt.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.